Lesson 5.1, we're using transformations to graph quadratic functions. The essential question is, how can I transform quadratic functions? Please write that essential question down. Can the path of a football kicked into the air be modeled with a linear function? Linear, recall what linear means. Linear means a straight line. So the answer is no, because if we kick a ball in the air, gravity is going to pull it back down. That's a parabola. So no, the ball's path is curved. First the ball goes up and then it goes down. The ball's path can be modeled by a type of nonlinear function called a quadratic function. So on this page, we talk about the equations for linear, quadratic in standard form, and quadratic in vertex form. Well, linear functions we're very familiar with. F of x equals mx plus b. Another way to think of that is like that. Quadratic function in standard form, f of x equals ax squared plus bx plus c. So again, that looks like a parabola. And then vertex form. Again, it's a parabola. I like to go like this. So we have two forms that we're going to deal with. We have standard form and we have vertex form. And notice they do look differently. So on this section, it shows a linear parent function. So there are various x values. You plug it in, you get your y values, you create a line. And then they're showing an example of what a quadratic parent function looks like. Notice that the graph of the parent function, f of x equals x squared, which we already know that that's the parent function for a quadratic because we studied that already. That is U-shaped. It's called a parabola. As with other functions, you can graph a quadratic function by plotting points with coordinates that make the equation true, meaning picking various x values, plugging it in to get the y values, and plotting the points. So we're talking about here the old-fashioned last resort. Let's see. It's saying graph g of x equals negative x squared plus 6x minus 8 by using a table. Make a table, plot enough ordered pairs to see both sides of the curve. This is what we're talking about. We're not going to use that. We're going to use what we know about transformations to graph our quadratic functions. But here, this is the last resort because it takes a lot of time and there's more room for error. So we grab various x values. Again, it doesn't matter what x values you pick. You plug them into the function and you get an output, which is your y values. Plot those points and you end up with this graph right here. Notice the negative out in front. What that does is that turns the parabola upside down. I call this a sad parabola versus a happy parabola. You can also graph quadratic functions by applying transformations to the parent function. Transforming quadratic functions is similar to transforming linear functions. Lesson 2.6, we did not do lesson 2.6. Translations of quadratic functions. Okay, so we're going to talk about horizontal translations, moving right or left, and we're going to talk about vertical translations, moving up or down. So if the parent function is f of x equals x squared, I always say if something is happening inside the parenthesis here, that means we're moving left or right. I also always say what's happening in the parenthesis is opposite of what you think. So if it's x minus h, that means we're moving to the right. X plus h, we're moving to the left. And what you're going to find in our example is, as we go through this, if it's an x plus h, that means your h is negative, because a negative times a negative is a positive. So that's what this is referring to. The up or down is much easier. That's the vertical shift. That's what's happening outside of the parenthesis after the x squared. It's a plus k, you're going up. If it's a minus k, you're going down. So let's do an example. I'm also going to write a few things here that I skipped over that I want to make sure I add to the notes really quick. Transforming. That's not what I wanted to highlight. Try that again. Transformations. What that means. Let's draw an arrow. That means we are moving, changing a function. That's what that means. And the other thing I want to point out, which we should already know, is that this function right here, which is the parent function, we know that the vertex of that function is 0, 0. Like I said, we've already learned that. One more thing I want to add to this. Horizontal is left or right. And this vertical refers to up or down. All right, let's do example 1. It says, using the graph of f of x equals x squared, describe the transformation, then graph. All right, well, the first thing I am going to do is I'm going to do a quick sketch of the parent function. We know that looks like something like this, right? I call that a happy parabola. Inside, there's something going on inside the parentheses. Remember, I said if it's plus, it's opposite of what you think. So that means we are going to the left 2, and that's because h is negative 2. It's x minus h. Boom, boom. That will make that plus. And k is negative 3. So that means down 3. So that's what I'm going to do. I'm going to change my color. I'm going to take my vertex, which is 0, 0 for the parent function, and I'm going to go to the left 2, 1, 2, and I'm going to go down 3, 1, 2, 3. By doing that, I created a new vertex, and that vertex is negative 2, negative 3, whereas this vertex was 0, 0. And now I can graph my new parabola. There we go. Supposed to be curvy and isn't being exact here in how I curved it or how I graphed it. Let's try something here. I don't like the way this turned out at all. I'm going to graph this one more time. Sorry about that. 0, 0. There we go. Right? We know that that's 0, 0. And we moved it to the left 2, down 1, 2, 3. Right there. We had a new vertex. And now our parabola. Crosses it, that's okay. There we go. There is our transformed parabola. Example 2. Oh, I think I forgot to do one thing back here. Just thought of it. No, I did. I described the transformation, left 2, down 3. Okay. So on this example, There's nothing happening in the parenthesis. There is no parenthesis. So we know that in this case, h is equal to 0. So we're not moving right or left. And we know that k is -5. So we are going down 5. So again, the parent function is right here. And the new function, I take that vertex and I go down 5. 1, 2, 3, 4, 5. My new vertex is 0 and -5. And there we go. There we go. So we graphed our new function and we described the transformation. We went down 5. Example 3 we are going to do in class. And now I'm moving on to example 4. And we're going to also do that in class. And I'm going to go down to here. Yeah. Okay. So we talked about transformations going to the left and right, up and down. Now we're talking about reflecting the graph across the y-axis and reflecting across the x-axis, or vertically stretching or compressing a graph. Notice it's a vertical stretch, compress. We do not do any horizontal stretches or compresses. And we don't use the reflection across the y-axis a lot. The most common is reflecting across the x-axis, which means that there's a negative sign out in front of the quadratic function and it flips upside down. And let me write a few things down here. When we're reflecting something across the y-axis, that means x changes. And when we reflect across the x-axis, the y values are changing. And so let's scroll down here. When we're talking about a vertical stretch or compression, what I like to think of it is, my trick is, again, if your a value, which is out in front, is negative, that has nothing to do with the stretching or compressing, because notice we're looking at the absolute value of a. A negative out in front only means the graph is flipped upside down. So if we're talking about a stretch, I think S stretch, the graph is getting skinny. A stretch, your absolute value of a is greater than 1, but your graph is getting skinnier than the parent function. When we're talking about compress, C, it starts with a C, I think of chunky. That's how I help students remember it. Compress means your absolute value of a is less than 1, but it's greater than 0, and the graph looks chunkier. So what I mean by that, I think of skinny, this means skinny. I think of chunky, it's wider. Example 5. Using the graph of f of x equals x squared. Let's just graph that. That's our parent function, vertex at 0, 0. Look how quick I graph it. It's not exact. Obviously, it's not exact, but I'm just doing a quick sketch. I'm going to describe the transformation, then I'm going to graph. Well, there's no parenthesis. So I know we are not moving right or left. There's nothing being added or subtracted out here. Not moving up or down. The only thing happening is you have a negative out front. So that negative out front right away, that means reflect over x axis. Remember, y is changing and it's flipped upside down. And the 1/2 refers to, so a The a value is obviously a negative 1/2. Remember, the negative goes with reflecting over the x-axis. And so since this absolute value, we know that, remember, we look at the absolute value of your a value. Since that's less than 1, we call that a compress by 1/2. So when we go and graph it, what I'm going to be looking for is, do you understand that your vertex is still at 0, 0? Because we're not moving right or left. We're not moving up or down. Do you also recognize that your graph is going to be flipped upside down? And you also recognize that it's going to be chunkier. Compress means chunkier. And yes, is this exact? No. But I see that you understand that the vertex did not change. It flipped upside down and the graph is compressed. Therefore, it is chunky. Example 6 saved for class. And now we are on the next part. If a parabola opens upward, it has a lowest point. If a parabola opens downward, it has a highest point. This lowest or highest point is the vertex. We've already talked about that. That's called a vertex. That's called the lowest point. Highest point. Those are the vertex. The parent function f of x equals x squared has its vertex at the origin. You can identify the vertex of other quadratic functions by analyzing the function in vertex form. The vertex form, remember we've talked about standard form and vertex form. The vertex form of a quadratic function is right here, where a, h, and k are constants. So you want to be very familiar with this vertex form. It's right there. A indicates a reflection across the x-axis and or a vertical stretch or compress. Remember, if A is negative, that means reflecting across the x-axis. Then the absolute value of A, if that's greater than 1, it's a stretch. If it's less than 1, it's a compress. There's our H. That indicates a horizontal translation, right or left. And K is vertical, up or down. Because the vertex is translated h horizontal units and k vertical from the origin, the vertex of the parabola, it has a new vertex now because we're moving it. It's not at 0, 0 anymore. It will be at h, k, and that's what we're referring to. When the quadratic parent function f of x equals x squared is written in vertex form, there it is. A is 1, h is 0, and k is 0. That makes sense. Example 7, we're going to only do number 1, and 2 and 3 we're going to do in class. Use the description to write the quadratic function in vertex form. We're going the other way. Instead of being given the new function and describing it, we're going to write it. So here's the parent function right there. We are going to reflect that across. So I'm going to highlight everything we're doing here. We're going to reflect it across the x-axis. We're going to translate 5 units to the left and 1 unit up. Wow, lots going on. So I know that if we're moving it 5 units to the left, I know h is a -5. I know k is a +1 because we're going up 1. And reflecting across the x-axis means there's a negative out in front. So I'm going to call this our new function, g of x, right now. Here's vertex form that we talked about. All right. Well, a is a -1, so all I need is a negative out there. It's x minus our h value plus 1. So our final answer then is going to be g of x equals -x plus 5 squared plus 1. And there it is. So as you can see, it's x plus 5, opposite of what you think. You're not going to the right. We were going to the left. It's always x minus whatever h is, and h is a negative 5. Just double checking everything looks good, and we are good. Save the rest for class. Video questions? Pause the video and do these problems.